there is a quiet truth, but one powerful enough to change the way you see your entire life. The human eye has never simply been a window opening onto the world. It is the place where the brain quietly constructs that world, moment by moment. Welcome to Sleep by Knowledge. Tonight, we're going to step into a journey that feels deeply familiar and strangely mysterious at the same time, because it is right there on your face, working for you from the moment you wake up until the moment your eyelids close, yet perhaps something you have rarely truly paused to listen to. That journey is the human eye. It is not only where light enters, it is not only the part of us that helps us read a line of text, recognize a face, or watch the sky change colour at the end of the day. The human eye is also the beginning of a far quieter kind of miracle. Every image you believe you are clearly seeing out there has actually travelled through a delicate process, where light touches the eye, signals are sent away, and the brain gently pieces them together into what we call reality. The deeper we go into the human eye, the more we begin to realise that vision is not just about seeing. It is how we locate ourselves in space, hold on to memory, recognise the people we love, sense the passing of age, and sometimes face the truth that what we see is not necessarily everything that truly exists. Tonight, we will slowly follow that journey, from the tiny structures hidden quietly inside the eye, to its limits, its changes over time, and even the deeper truths about how human beings exist within this vast world. And if you stay with me until the end of the video, what lingers may not only be knowledge about the human eye, but a very different feeling, that throughout your whole life, you have never really seen with just your eyes, but with an entire system that is fragile, extraordinary, and deeply human. So now, lower the brightness of your screen just a little, let your shoulders relax, and come with me into a quiet journey inside the human eye. And when we begin to look slowly and carefully at the human eye, we soon realise something both simple and strange. The human eye does not stand alone at the front of the face like two small windows opening onto the world. It is the front end of an entire nervous system working quietly behind the scenes. We often say that we see with our eyes, but science tells a much fuller story. Light may enter the eye, but an image only truly becomes a world when that signal is received, processed, relayed, and finally interpreted by the brain as a meaningful scene. In other words, the human eye does not simply hand us a picture. It begins an ongoing conversation between light, neural tissue, and the brain. That may sound abstract until we think about a very familiar experience. You open your eyes in the morning and see the ceiling, the curtains, the chair in the corner, the pale light touching the surface of the table. Everything seems to appear instantly, completely, seamlessly, as though the human eye simply opens and the world flows right in. But in truth, no image travels straight from the world into consciousness on its own. There is light reflected from objects. There is the cornea and the lens helping focus that light. There is the retina receiving it. There is the optic nerve carrying information away from the eye. And only after the brain finishes its part of the work do we get the feeling that we are looking at a quiet room with distance, depth, and the position of each object clearly in place. Human sight, then, is always a finished neural product, not just the surface response of an organ. Throughout that entire journey, the retina of the human eye is far more remarkable than most of us were ever taught to imagine. Many people unconsciously think of the retina as something like a strip of film, or the sensor in a camera, a place where light lands and waits to be passed along. But neuroscience shows that the retina is real neural tissue. It is even considered an extension of the brain itself, and during embryonic development, it arises from an outgrowth of the forebrain. That means deep inside the human eye, we do not just have a surface that receives light. We have a neural structure already participating from a very early stage in the analysis of the world. When we take that in slowly enough, we begin to understand why research on the retina often helps scientists understand the brain itself. Because at some level, looking at the retina is also looking at part of the central nervous system resting in the most accessible place on the body. And once light reaches the retina of the human eye, the story does not stop with turning light into electrical signals. It is true that the light-sensitive cells begin the process of signal conversion, but after that, the retina contains an entire network of other nerve cells that continues to filter, emphasize, compare, and separate important features of the image before the information is sent to the brain. Put more gently, the retina of the human eye does not wait for the brain to do all the work. It has already begun processing part of the scene on its own. It helps highlight edges, differences between light and dark, colour, contrast, and many of the clues the brain will later need in order to assemble an orderly world. So even at the back of the eye, interpretation has already begun. We think we have only just looked, but in truth, the human eye has already been quietly selecting information before we're even aware that we are seeing. At this point, the human eye begins to move far away from the image of a mechanical camera. A camera records almost everything that enters the lens, then leaves the viewing or later processing to a person or to software. But the human eye is different. It does not send the world into the head exactly as it is. It compresses, selects, prioritizes, and organizes signals in ways that fit human biology. That is why in the same scene the brain can recognize motion, differences in brightness, or the location of an important object much faster than if it had to go back and inspect every single point of visual data. What we call human vision, then, is not a neutral copying process. It is an ongoing process of filtering and constructing meaning. The human eye opens reality to us, but it never delivers reality in its raw form. It always hands the brain a version that has already been prepared for further completion. Then, from the retina of the human eye, the signal enters a path far longer than the immediate feeling we usually have when we look at something. Those electrical signals travel through the optic nerve, a massive bundle of nerve fibers made up of more than 1 million fibers, then continue through the optic chiasm, the optic tracts, the lateral geniculate nucleus in the thalamus, and only after that are sent to the visual cortex in the occipital lobe for further processing. That detail alone is enough to change the way we think about seeing, because it turns out that the quiet scene in front of us must travel through an entire complex neural network before it becomes a vivid experience inside the mind. The human eye, then, is not the endpoint of vision. It is simply the place where vision begins its journey into the brain, where every beam of light is turned into pulses of information racing to find meaning. And once we understand that pathway, we also understand why seeing is not the same as merely having the eyes open. A person may still have human eyes present anatomically, the pupils may still respond, light may still enter, but if the regions of the brain responsible for visual processing are damaged, the experience of seeing can still change profoundly or be severely reduced. This is described in brain-based visual disorders, where the main problem does not lie in the eyeball itself, but in the parts of the brain responsible for processing images. By this point, vision becomes a much humbler thing. We no longer think of the human eye as two independent devices hanging at the front of the body. We begin to understand that every moment in which we recognize a familiar face, read a line in a book, or find an old road again is the shared achievement of both eye and brain. Without one side, the other cannot create a complete act of seeing on its own. Maybe that is also why the human eye remains so astonishing when we place it beside ordinary daily life. You may be driving on a calm afternoon, and within just a few seconds the visual system has already done a whole series of things your conscious mind barely notices at all, keeping the image from blurring when your head turns slightly, helping you sense the distance to the car ahead, recognizing a road sign in the distance, distinguishing the shadow of a tree across the road from an object that is actually blocking your path, then continuously updating all of that so you still feel as though you are simply looking. That feeling of simplicity is the most beautiful proof of just how refined the human eye really is. The things that work most efficiently in the body are often the things we notice the least. The eyes rarely ask to be praised. They simply let the light in, pass the signals along, and allow the brain to turn a vibrating world into a space with order, sequence, nearness, and distance. One of the clearest expressions of that cooperation lies in the fact that the human eye almost always works as a pair. We can live with one eye, but when two eyes are directed toward the same object, the visual system receives two slightly different images because of the horizontal placement of the eyes on the face. That very small difference, called binocular disparity, helps the brain infer depth and create the feeling of three-dimensional space. Put more simply, the human eye does not receive two identical copies of the world. Each eye looks from a slightly different angle. And the brain, instead of treating that as useless duplication, transforms that difference into the ability to estimate distance, sense depth, and judge the location of objects in space. So when we reach for a cup on the table without giving it much thought, behind that quiet movement is a very precise coordination between two retinas and multiple layers of neural processing. But the coordination of the human eye is not only important when looking far away, it is especially necessary in our closest moments too, such as when we read a book, thread a needle, look at a phone screen, or admire a flower beside the window from just a short distance away. When looking at something nearby, both eyes must aim at the same point with enough precision for the brain to merge the two images into one. If that coordination is not smooth, a person may experience blur, double vision, or eye strain when working at close range. That reminds us that the human eye does not simply need to be healthy in the sense that each eye sees clearly on its own. It also needs to work in harmony with the other, like two musicians keeping the same tempo in order to create a calm and steady melody. Normal vision, then, is not only a matter of light being right or wrong, it is also a matter of synchrony, compatibility, and cooperation. The deeper we go, the more fascinating it becomes that the human eye does not send the brain a single anonymous block of information. Right from the retina, different streams of signals are already carrying different kinds of information. Some pathways are especially sensitive to changes in brightness and contrast. Others help colour become more distinct. Some neural mechanisms in and beyond the retina are especially important for motion, position, and orienting responses. So when a leaf trembles lightly outside the window, or when car lights sweep by in the night, the human eye does not simply register that there is light. It separates the world into qualities that can guide action. What is changing in brightness? What is moving closer? What is background? What is an object standing out from the background? That may be why human vision feels both poetic and practical at the same time. It gives us the sunset, but it also gives us the path we need in order to walk without falling. At this point, we can pause for a moment and look back at our own experience of seeing today. Maybe you looked at a clock, the face of someone you love, the rim of a teacup, these very lines of text, and never once thought that the entire chain of those actions depended on such a deep relationship between the human eye and the brain. We usually pay attention to what causes pain, strain, or malfunction. But when the eyes are working normally, we almost forget that normal itself is a marvel. Inside those two small eyeballs is exquisitely refined neural tissue, a long signalling pathway, and a processing system so complex that as long as it runs smoothly, we assume everything must naturally be this way. But it is not. The gentle ease of everyday seeing is the result of a biological architecture shaped with extraordinary depth through evolution and development. And perhaps this is the most important thing to carry with us before we go even deeper into the human eye. Every time you see an object, you are not only opening your eyes toward the world, you're also witnessing the brain complete a quiet act of construction. Light is only the beginning. The retina of the human eye receives and preprocesses information. The optic nerve carries that information away from the eye. Deeper neural stations continue organizing the signals. And only then does the brain give you the feeling that a world is appearing clearly, steadily, and right in front of you. Once we understand that, we no longer think of the human eye as two cameras attached to the body. We begin to see them more truthfully for what they are. Two living gates where the brain touches light in order to build the reality we call life. If, in the last section, we came to realize that the human eye is not just two passive windows but the front end of an entire nervous system, then now we can slow down even more and follow the very first thing that truly touches the human eye: light. Every story about vision begins here. Not with images and not with meaning, but with electromagnetic waves reflected off the surfaces of objects, moving through still air and arriving at the very front surface of the human eye. That is why the science of vision, at its core, is always the story of light meeting living tissue. And in that moment, the human eye does not see right away. It only begins receiving the raw material that the brain will later use to construct the world we assume is simply appearing in front of us. Try to imagine a beam of light leaving a bedside lamp in a room that is just dark enough, sliding past the edge of a blanket, touching the spine of a book, and then bouncing back into the air. That beam of light does not carry the meaning of the words in the book, and it does not carry the warmth of the room. It only carries physical information about colour, brightness, shape, and surface texture. When that beam reaches the human eye, the first place it meets is the cornea, the transparent layer at the front of the eyeball. The the cornea is not a flat, emotionless sheet of glass. It is curved, transparent, and it is precisely because of that dome-like shape that it bends light the moment light touches the eye. Put more gently, the human eye begins organising the world not from somewhere deep inside, but right there at the outermost layer, the one that seems the most delicate. This is also one of the most beautiful truths about the human eye. Most of its focusing power does not come from the lens, as many people assume, but from the cornea itself. According to the American Academy of Ophthalmology, about 70% of the eye's focusing power comes from the cornea, while the lens contributes the rest in a more flexible way. That means that right at the very first gateway, the human eye already has a powerful optical surface doing the heaviest part of the work, bending light in the right direction. When this happens normally, we do not feel a thing. We simply assume that we are seeing. But deep within the optical logic of the body, the cornea is carrying out an incredibly delicate task. It receives light spreading out from the world and begins bringing it into an order precise enough for the rest of the human eye to continue the job. After the cornea, the beam of light moves through a fluid-filled space in the front part of the eye, then approaches a coloured ring that almost everyone thinks they already know well, the iris. We usually notice the iris only as the part that gives the eye its blue, brown, grey or amber colour. But in the human eye, the iris is not just colour. It is a living mechanical structure whose job is to adjust the size of the pupil. And the pupil, the dark centre of the eye, is not a separate object at all. It is an opening. In other words, that dark area we see in the centre of the human eye is really a doorway. That doorway can widen or narrow, not according to our conscious will, but according to the amount of light in the environment. When the light is bright, the iris makes the pupil smaller to reduce how much light enters. When the light is dim, the iris widens the pupil to let in more light. That is why the human eye always carries within it a very quiet rhythm of adaptation. If you have ever stepped from a dark room into bright sunlight and instinctively squinted, that is not just a moment of discomfort. It is part of the eye's protective and light-regulating system. On the other hand, when you turn off the lights and sit quietly in the dark, you notice that the human eye needs a little time before the room stops feeling completely black. It is not because the darkness has changed, but because the visual system is gradually adapting. The pupil opens wider, neural mechanisms slowly adjust, and the entire experience of seeing in darkness begins to shift. Light, then, does not simply enter the eye. In the human eye, light is always being measured, controlled, and allowed in at a level that fits the situation. Then, after passing through the darkness of the pupil, the beam of light moves closer to the lens. If the cornea is the first surface that receives light and provides most of the focusing power, then the lens is the more flexible part, helping the human eye adjust focus for near and far distances. The lens is clear, sits behind the iris, and works with the cornea to bring light into proper focus on the retina. When we look far away, that optical setup is one thing. When we look at something close, the lens has to change shape in a subtle way to increase its focusing power. We usually do not feel this happening consciously, but it is taking place thousands of times in ordinary life, every time the human eye shifts from a distant mountain range to the words on a screen, or from the face of the person in front of us to the rim of a teacup just inches away. This also explains why vision in the human eye is always an art of balance between stability and flexibility. If the optical system of the eye were completely rigid, we would only see clearly at one fixed distance. But because the lens can change shape to help adjust focus, the human eye can live in a world where distances are constantly changing without causing our conscious experience to break apart. You look out the window at a tree branch, then down at a watch, then back up at a face. We call all of that seeing, but inside the human eye, countless tiny adjustments have taken place to keep the world from dissolving into layers of blur. The calmness of everyday vision, when you really think about it, is the result of many very small changes happening too quickly for us to notice. And then, after being bent once by the cornea, allowed through by the pupil in the proper amount and refined further by the lens, light still has not completed its journey through the human eye. It still has to pass through the transparent interior of the eyeball in order to reach the retina, the light-sensitive tissue at the back of the eye. This is a moment worth remembering if we want to understand vision more deeply. Because in everyday experience it feels as though the world is out there and then simply goes straight into awareness, but biologically, light has to travel a long way through the human eye before it reaches the first place where sensory cells are waiting. The retina is in the back, not in the front. Seeing, then, does not begin at the surface of the eye, but in a layer of neural tissue lying deep at the end of light's journey. When the beam of light finally reaches the retina, one basic optical principle of the human eye has been fulfilled. Light must be focused precisely enough on the retina for the image to be sharp. If the focal point falls in front of or behind the retina, vision will not be as clear as it should be. That is the foundation of common refractive errors, where the shape of the eye, the cornea, or changes in the lens cause light not to land in the right place. But even before we talk about those problems, this principle alone is already astonishing. The human eye does not need a screen placed halfway along the path of light. It needs a very specific target at the back of the eye, and the entire optical system in front is organized to deliver light to exactly that point. That is how a real-world scene can be turned into neural signals in a reliable way. At this point, there is one detail that can make a person fall quiet when it is told slowly enough. The optical image that lands on the retina of the human eye is not the final, complete copy of the world. It is only a version of light that has been focused according to the laws of optics. When light touches the retina, the light-sensitive cells begin transforming it into electrical signals. From there, the signals leave the retina through the optic nerve and travel toward the brain. Put more gently, the entire journey through the cornea, iris, pupil and lens has only brought the human eye to the threshold of seeing. Vision does not end there. It has only just acquired the raw material it needs to begin. Once we understand that, we stop talking about light as though it magically becomes an image inside the eye. Light only becomes neural data at the retina, and meaningful imagery has to wait for the brain to take part. Maybe that is why the human eye always feels both physical and miraculous at the same time. Physical, because everything follows very clear rules. Light must pass through transparent tissue, it must be bent, its intensity must be controlled, and it must be focused at the right location. But at the same time, the entire process is so delicate that we can live our whole lives without ever really hearing it at work. Think of someone sitting under warm yellow light at the end of the day, quietly reading a book. In those peaceful minutes, countless beams of light are leaving the page, entering the human eye, being bent by the cornea, regulated by the iris as they pass through the pupil, assisted by the lens for proper focus, and only then reaching the retina. The reader does not feel any of those intermediate steps. They only feel the meaning of the words. And that is the quiet beauty of the human eye. It hides almost all of its optical labour so that lived experience can take centre stage. But the optical system of the human eye does not only help us see things that are distant or useful, it also shapes the way we live through the most ordinary moments. When you step outside in the morning and everything feels too bright for the first few seconds, that is the iris and pupil working together to protect the eye from a sudden increase in light. When you look from the road ahead to the navigation screen in your car, that is the lens helping shift focus. When you walk into a dark movie theatre and have to wait for your eyes to adjust, that is the entire visual system of the human eye adapting to new lighting conditions. These may sound like tiny things hardly worth mentioning, but they show us that vision is not a straight, uninterrupted stream. It is a continuous series of adjustments, where the human eye is always negotiating with light to keep the world clear enough to see and safe enough to live in. As we grow older, the journey of light through the human eye begins to reveal more changes, and this is something especially familiar to adult audiences. According to Medline Plus, over time the pupil tends to become smaller and slower to respond to changes in light and darkness, while the lens becomes more yellow, less flexible, and may gradually turn cloudy. That's why many people find close reading harder, bright glare more uncomfortable, or night driving more tiring. Those changes do not stop light from making its journey, but they do make that journey less smooth. And what matters here is that understanding this often brings comfort rather than fear. Because once we realise that the human eye changes over time as a natural part of life, we stop blaming it for no longer working the way it did at 20 years old. If we look at that whole process as a story, then the story of a single beam of light through the human eye is actually very short in time, but very long in meaning. It travels from the outside world to the cornea, from the cornea to the pupil, from the pupil to the lens, from the lens to the retina, and only from the retina does it continue as a signal for the brain to decode. Each stage follows a very clear logic, but together they create an experience so smooth that we forget how complex it really is. Maybe that is what makes the human eye so worthy of wonder. It does not need to display its work. It simply lets light pass through, then hands the rest to the brain, so that what remains inside us in the end is not a beam of light, but a face, a room, a line of trees, a sense of depth, a memory just beginning to form. Before we move deeper into the next layers of vision, perhaps this is the thought worth holding quietly in the heart. Everything begins with light, but in the human eye, light is never the end of the story. It is only the first visitor to arrive. The cornea receives it, the iris weighs it. The pupil opens the way for it. The lens adjusts its path. The retina waits for it at the end of its visible journey. And after all of that, the brain gently turns it into the world we live inside. The more clearly we understand that journey, the more clearly we see the central truth of the whole story. The human eye does not simply let us see the world. It gives the brain the raw material it needs to build that world out of light, moment by moment, in rhythms so gentle, so precise, and so quiet that they almost never ask to be noticed. When light finally completes that transparent journey and reaches the retina of the human eye, a very quiet boundary has been crossed. Up to that point, everything has still been optical. It has still been a matter of light being bent, regulated, and guided to the place where it needs to go. But from the moment light touches the retina of the human eye, the story is no longer only about physics. It becomes biology. It becomes neuroscience. It becomes the first step of what we later call seeing. If the cornea, iris, pupil, and lens are the guides that lead light along the way, then the retina of the human eye is the place where light is translated into a language the brain can understand. And that is one of the quietest, yet most astonishing transformations in the entire body. We often get the feeling that the retina of the human eye is like a surface at the back of the eye, where an image lands the way a photograph is captured. That feeling is easy to understand because it is simple and convenient for the imagination. But the truth is far more delicate than that. The retina of the human eye does not merely receive an image. It is living neural tissue, a highly organized layer of cells where light is not only received, but also selected, processed, and transformed. Put more gently, the retina does not wait for the brain to do all the work. Right there in the retina of the human eye, part of the work of separating and interpreting the world has already begun. Some cells detect light, some cells pass signals along, some cells adjust, inhibit, sharpen, or quiet things down. So when we say that the eye sees, that statement is still incomplete. It would be more accurate to say that the human eye begins understanding light at the level of the retina, even before the brain receives the rest. Maybe one very ordinary way to feel this more clearly is to look at a page in a book under soft light. You can read the small words in the centre of the page fairly clearly, but unless you move your eyes, you cannot precisely describe the words sitting near the far edges of the paper. You know they are there. You know the block of text continues to both sides. But the clarity is not evenly distributed. That small experience alone reveals an important truth about the retina of the human eye. It does not give every point in a scene the same level of detail. Human vision always has a centre of emphasis. It always has a central area that is prioritised, and a peripheral area that works in a different way. We tend to think we are seeing the entire scene with equal sharpness, but in truth, the human eye gives only a very small portion of the visual field the highest possible clarity, while the rest is handled through a different strategy, one better suited to survival and orientation in space. At the very centre of the retina in the human eye is a special region called the fovea. This is the area responsible for the sharpest vision, where cone cells are packed at very high density, and where fine detail is resolved most clearly. It is because of this region that we can read small print, thread a needle, recognise subtle facial expressions, distinguish the fine outline of a leaf, or clearly see a bright star in the brief moment when the eye lands exactly on it. But what surprises many people is that this sharpest area is not wide at all. It is very small. That means the most refined part of human vision occupies only a very modest region. While most of the scene we think we are seeing clearly is actually built through very rapid eye movements and through the brain stitching together fragments of information. The world, then, does not appear before the human eye as one evenly detailed picture. It is more like a surface the eye keeps scanning, while the brain patiently assembles each part into the seamless feeling of a whole. In that central pit, the cone cells of the retina in the human eye play the leading role. Cone cells work best in daylight or in strong illumination. They allow human beings to distinguish colour and fine detail. Because of cone cells, the evening sky is not merely light or dark, but can become soft blue, pale gold, thin pink or deep violet. Because of cone cells, the human eye can tell the difference between the dark wood of an old table and the warm brown of a cup of tea under a lamp. Because of cone cells, we can read black words on white paper, see the delicate veins of a flower petal, and notice small shifts in the tone of a familiar face. In other words, the richly coloured, finely detailed world that human beings love so much is built largely through the work of cone cells in the central region of the retina in the human eye. But if the human eye had only cone cells, our lives would be very different and probably much more difficult in dim conditions. When the light grows faint, such as at dusk in a room lit only by a bedside lamp, or on a country road with very few streetlights, cone cells are no longer the strongest force at work. That is when rod cells in the retina of the human eye begin to show their value. Rod cells are more sensitive to light and work better in darkness or near darkness, but they do not help us distinguish colour with the same delicacy as cone cells. That explains why in low light, human beings tend to perceive shape, motion, and direction better than colour. A dark blue shirt and a brown shirt may look clearly different in full light, but in dim conditions the human eye may register them only as two similar dark forms. That is not the eye performing badly for no reason. It is the strategy of the retina, where rod cells prioritise whether there is light or not, whether there is an obstacle or not, whether something is moving or not. What is fascinating is that rod cells and cone cells in the retina of the human eye are not distributed in the same way. Cone cells are concentrated in the centre, while rod cells are far more abundant in the periphery of the retina. That arrangement creates a very quiet but extremely important feature. The human eye uses the centre to inspect detail, and the periphery to keep watch over the larger world. When you're walking at night and suddenly notice movement from the corner of your eye before you can identify what it is very likely that the peripheral retina alerted you first. When you look straight at a candle but still know that someone just walked past nearby, that is the periphery doing its job. The brain does not ask the peripheral field to read small print or distinguish fine shades of colour. It relies on the periphery to detect motion, direction, and changes large enough to guide behaviour. In the human eye, each region does not see in the same way, because each region has been given a different task. That is also why the human eye does not look at everything with the same kind of attention. The central region is like the place where we direct our focus most deliberately. The periphery is like a gentle field of awareness surrounding that focus. A person sitting under a desk lamp reading a book uses the fovea to follow each word, but the peripheral retina of the human eye still quietly informs them where the window is, where the chair is, whether a shadow just moved across the hallway, or whether a breeze just stirred the curtain. Without the central region, we lose the sharpness needed for delicate tasks. Without the periphery, we lose the sense of being properly placed in space. Ordinary human vision, in the end, is the harmony of two different ways of knowing, beautifully complementing one another. By now, we may begin to realise that the human eye has never promised to give us a perfectly complete picture in the mechanical sense. It gives us a picture with a structure of priorities. That explains why we have to move our eyes constantly without even noticing it. Very fast eye movements, called saccades, bring the fovea from one important point in a scene to the next. You look at someone's face, and within moments your eyes have already shifted from their eyes to their mouth, to the line of their cheekbone, to a small detail on their shirt, and then back again. The human eye does not look once and finish the job. It gathers information in small, rapid pulses, while the brain puts everything together to create the feeling that we have seen the whole scene instantly. That is how a room, a face, or a newspaper page appears as a complete whole, even though the retina gives the clearest detail only in the centre at any given moment. The more we think about this, the more the central truth of the whole story comes into focus. The human eye does not hand the brain a fully packaged world that is already complete. The retina only sends out streams of signals arranged according to its own strengths and weaknesses. One place is rich in colour. One place is sensitive to low light. One place is extremely sharp. Instead, we begin to see that structure as profoundly wise. If the entire retina were as sharp as the fovea, the neural cost would probably be far too great. If the entire retina were designed only for darkness, we would lose the world of colour and fine detail. The human eye chooses a division of labour, and it is precisely because of that division that vision becomes both refined and efficient. There is a very small experience that helps us feel the role of rod cells in the retina of the human eye. If you're looking at a rather faint star in the night sky and try to stare directly at it, sometimes it becomes harder to see, but if you look slightly to one side of it, the star may become easier to detect. This happens one brief, and human sight, even when we lift our eyes toward a distant star, is still the result of how that map is being used. On the other hand, if you try to read a small line of text without placing it at the centre of your gaze, you will find it nearly impossible. This difference between centre and periphery is not a flaw, it is an organising principle. It is that principle that allows the human eye to read tiny print on a prescription label while still noticing that someone has just entered the room from the side. If every signals from the light-sensitive cells are transmitted through layers of intermediate cells before reaching the ganglion cells, whose axons come together to form the optic nerve. It is within these layers that contrast is emphasized. The edges of objects are sharpened, and important differences are filtered out. That helps explain why the human eye is often so sensitive to boundaries between light and dark, and why it can quickly recognize a striking shape against a background. A white glass sitting on a dark wooden table is not seen clearly only because it reflects light. It is also even colour, which we usually take for granted in the human eye, is not as simple as different wavelengths of light landing on the retina. The cone, it is the result of how the retina of the human eye receives information and how the brain interprets those differences. Looking at a ripe orange under morning sunlight, looking at a leaf late in the afternoon, looking at the sea beneath grey clouds, all of those colours that seem to already exist out there must still pass through a subtle biological process within the eye and brain. The more the brain, this is very close to real life. When we speak with someone we love, we place their face at the centre of our gaze in order to read emotion, but the periphery still tells us where the cup of tea is, whether the door is open or closed, and whether someone is walking closer. The human eye, then, does not only help us see objects, it helps us place our focus on what matters while still remaining connected to the larger setting. And if we do not see in darkness the way we see in daylight. But from all of those limits, the brain can still build a reality that is remarkably coherent, trustworthy enough for us to read, walk, drive, recognize the people we love, and live an entire life without often stopping to ask how any of it is possible. Deep down, the human eye does not give us perfection. It gives us a system optimized for real life. And perhaps that is exactly what makes it so moving. It does not try to do everything. It does exactly what human beings most need in order to live in this world. So there is a center for detail, there is a periphery for orientation, there are cone cells to provide color and sharpness, there are rod cells to preserve dim light and motion in the night, there is a retina to receive, organize, and transform. And there is a brain behind it all, patiently assembling those fragments of signal into the world we assume we see instantly. The deeper we go into the retina of the human eye, the more clearly we see the core truth of this entire journey. Human vision always has a center, always has limits, and it is precisely from those intelligently organized limits that reality becomes vivid, clear, and livable. From the moment the retina of the human eye has just managed to turn light into signals, the world begins to take on another quality, one so familiar that most of us no longer stop to wonder at it. That quality is colour. We tend to think colour is already sitting there on the surface of things, as if a leaf is simply green on its own, an orange is naturally orange, and the sky is naturally pale blue at the beginning of the day and deep red at the end of it. But in more precise biological terms, colour only begins to take shape when the human eye uses cone cells to receive different wavelengths of light, and the brain then combines and sorts those signals into what we experience as colour. Put more gently, colour is not only out there. Colour is the meeting point between light, the retina of the human eye, and the brain quietly interpreting it all. The three kinds of cone cells in the retina of the human eye are sensitive to different wavelength ranges, often described as being closest to red, green, and blue. They do not work like three separate buckets of paint. They work more like three overlapping streams of signals, each one responding more strongly to a certain range of light. When a beam of light reflected from the skin of an apple reaches the retina, the human eye does not receive a label that says this is red. It only receives a pattern of activation across the cone cells. Then the brain reads that pattern and gives us the feeling of a familiar colour. That is why colour is not simply a property of an object. It is the result of how the human visual system encodes and reads signals of light. This explains why a scarf can look different under the noon sun, under the shade of a tree, under the warm yellow light of a living room, or under the white lighting of a supermarket. The fabric itself has not changed very much over those few short hours, but the spectrum of light falling on it has changed. The light reflected into the human eye has changed with it, and so the signals reaching the retina and then the brain are different as well. We often say a colour looks prettier under a certain kind of light, but if we slow down, that statement is also telling us that the human eye never sees colour in a way that is separate from the light source. When the light changes, the experience of colour changes too, because what the eye receives is always light after it has passed through the circumstances around it. Perhaps nowhere is that clearer than when we watch a sunset for a long time. In that moment, the human eye is not only admiring a beautiful view, it is receiving a sky whose light spectrum has changed because the sun is lower, because the atmosphere scatters more of the shorter wavelengths, leaving more yellow, orange and red light to reach the eye. The cone cells of the human eye respond to that change, and then the brain combines those signals into the deeply emotional experience we call a sunset. What makes that moment feel so profound is not only the sky itself, but the fact that the human visual system is subtle enough to turn physical differences in light into an experience that feels almost meditative. The more we understand that mechanism, the more we see that the human eye does not diminish the beauty of the world by analysing it. On the contrary, it shows us how that beauty passes through biology and becomes even more intimate. But the world built by the human eye is not made of colour alone. It also contains detail, and that detail is not distributed evenly, as we have already begun to notice from the retina itself. When we look directly at a leaf near a window, we can see its veins, its edges, the thin shadows, and the light passing through it. But if we do not move our eyes and try to detect that same level of fine detail at the edge of our field of view, the human eye cannot do it. This is not a flaw, it is a strategy. Cone cells are heavily concentrated in the central region, helping the human eye achieve higher detail vision in bright light, while other regions are given other tasks. That is why the world in front of us is always clearer in the centre, yet broader because of the periphery. The brain receives that division of labour and turns it into the feeling that everything is present at once. Then when the light grows dim, a different kind of world begins to appear. Rod cells in the retina of the human eye are more sensitive to light, so they help us function better in darker conditions, but in exchange, the ability to distinguish colour decreases noticeably. That is why a road that is full of colour during the day can become almost monochrome at night, and why a room lit only by a bedside lamp can still show us objects, but with far less richness. The human eye does not work the same way in every lighting condition. It changes its priorities. In bright light, it prioritizes colour and detail. In darkness, it prioritizes the detection of light, shape and motion. We think we're looking at the same world all day and all night, but in truth, the visual system is quietly changing the way it builds that world depending on how much light it has. Maybe everyone has felt that while driving at night. Road signs are still there, the edge of the road is still there, the lights of other cars still pass by, but the feeling of seeing is not the same as it is during the day. Colour becomes less rich, darkness feels denser, and strong lights can become painfully glaring. It is not that the human eye suddenly becomes weak at night for no reason. It is because the part of the visual system that is stronger in low light has to carry more of the load, while the system for colour and fine detail is no longer working under ideal conditions. In moments like that, we can clearly feel a deeply human truth. The human eye is always trying to give us enough information to keep living in the world, even when it cannot give us the most vivid version of it. The world that the human eye builds is not made only of colour and sharpness. It also contains motion, and motion is especially important for survival. Very early in evolution, any creature able to detect something rushing closer, sliding across, or changing position quickly would have had a much better chance of responding in time. Perhaps that is why the human visual system is so sensitive to motion, especially in the periphery, where it does not need to read tiny details but does need to catch changes big enough to alert the body. If you have ever been sitting still and suddenly noticed a passing shadow from the corner of your eye before you even turned your head, that is because the human eye does not wait for the world to hold still before recognizing it. It is especially good at noticing when something is no longer still. In the retina of the human eye, rod cells are not only useful for low light, but also play a strong role in detecting motion. That is why the peripheral part of vision is often more sensitive to something moving than to something standing still. So a cat crossing the edge of the road, a branch trembling lightly by the window, or a hand just lifting at your side often enters your awareness before you even turn to look directly at it. In that sense, the human eye does not merely gather scenery. It watches over the environment. It keeps a soft layer of warning around the centre of our attention so that the body is not cut off from changes that matter. And yet, detecting motion is only half the story. The other half is how the human eye still gives us the feeling that the world is stable even though our head keeps turning, our body keeps moving, and our eyes are constantly shifting back and forth. When we walk, go downstairs, turn when someone calls our name, or look from a car window to a road sign, the image on the retina should, in theory, be jolting and sliding all the time. But in subjective experience, the world does not shake with every movement of the head. Part of the reason lies in the vestibulo-ocular reflex, a mechanism that makes the eyes move in the opposite direction of the head in order to keep the image relatively stable on the retina while we are moving. Because of that, the human eye does not only know how to receive light, it also works together with the balance system to keep vision steady inside a body that is always in motion. This is especially easy to feel when walking downstairs. You almost never need to stop at each step and measure it. The human eye, working together with the head, the inner ear, the neck muscles and the brain, gives you a fairly reliable sense of where each step is in relation to your feet. If the mechanisms for image stabilization and depth perception were not working smoothly, walking downhill or going down a staircase would become much slower and far more uneasy. Something as ordinary as placing your foot on the next step is actually the result of countless neural calculations involving distance, posture, motion, and the stability of the visual frame. The human eye, then, does not only give us a beautiful scene to admire, it helps us move through the world without falling. And when we speak of distance, we cannot avoid stopping at depth. The two human eyes sit side by side on the face, separated by just enough space for each eye to view the world from a slightly different angle. The brain receives two images that are similar but not perfectly identical, and combines them into a sense of three-dimensional space, helping us judge what is near, what is far, which surface bulges outward, which edge curves inward, and where a cup is in relation to the fingertips reaching toward it. This ability is often called binocular vision, and it is one of the foundations of depth perception. Because of it, the human eye does not merely give us a flat picture. It gives us a space we can step into, reach through, and live inside. That is why very simple acts such as pouring water into a cup, sliding a key into a lock, parking close to the curb, or putting out a hand to catch a falling object depend so heavily on the way the human eye constructs depth. We rarely think of that as a special ability because it feels too ordinary. But if we slow down, we can see that it is a marvel. Two slightly different pictures, one from each eye, together with other cues such as relative size, shadows, overlap, and the movement of our own body, are combined by the brain into a highly coherent experience of space. The human eye, then, does not only gather light, it gathers clues that allow the brain to turn light into distance. There is another delicate point that makes this story even more beautiful. The two eyes are not always the only source of depth. Even with one eye closed, a person still has many other cues for judging distance, such as perspective, a nearby object blocking a farther one, the familiar size of things, and relative movement as the body moves. But when both human eyes are working together well, the sense of depth becomes far more natural and trustworthy. That reminds us that vision does not rely on a single trick. The brain is always gathering many different signals from the two retinas, from motion, and from past experience, in order to build a space stable enough for everyday life. The deeper we look into colour, detail, motion, and depth, the more clearly we see that the human eye does not treat everything entering it equally. It prioritises what matters to the body. A strong edge between light and shadow often draws more attention than a flat, uniform surface. An object rushing closer is detected faster than a still object far away. The edge of a stair matters more than the paint on the wall beside it when we are walking in low light. This does not make vision poorer. On the contrary, it makes vision practical in an extremely intelligent way. The human eye was not made to copy the world like a scanner. It is organised to help a living body move through that world. We can feel that very clearly on a rainy night while driving. Oncoming headlights spread into blurs, painted road lines sometimes fade, the windshield reflects layers of small lights, and the distance to the car ahead has to be judged in an environment that keeps changing. In that moment, the human eye is no longer admiring colour for the sake of beauty. It is prioritising what matters for safety, which motion is approaching, where the edge of the road is, which brake light has just come on, and which distance is closing. That same visual system that can slowly admire the colour of leaves during the day can, at night, immediately shift into a mode that emphasises what matters for action. The world, then, is not only seen, it is filtered according to what the body needs to know first. And then, when we return to a softer scene, like sitting quietly and looking at the sky at the end of the day, all of those things are still happening, only more gently. The cone cells of the human eye are reading subtle changes in light. The mechanisms stabilising the visual frame are helping the cloud stay steady despite each small breath and tiny movement of the head. Both eyes are giving the brain clues about the distance between the tree near the window and the streak of cloud far away. The periphery still knows that a bird has just crossed the edge of the sky. We call that watching the sunset. But at a deeper level, it is a moment when the entire visual system is working so completely that all we are left feeling is the quietness of the world. If we look back across this whole stretch of the journey, we can see that the human eye has never simply been the place where light enters. It is a colour filter, a motion detector, a depth reference system, a partner to the balance system, and a source of raw material the brain uses to build a world that is both clear and selective. Colour appears because the brain blends signals from cone cells. Detail appears because the centre of the retina is prioritised. Motion appears quickly because the periphery and the pathways shaped for survival stay alert. Depth appears because the two eyes send back two slightly different views, and the brain fuses them. The world the human eye gives us, then, is not only clearer than we think, it is also more carefully selected than we think. Perhaps this is the thought worth holding on to gently before we go any deeper. Every time you notice a stair lower than where you're standing, recognise a car approaching in the night, or fall silent at the sight of the sky changing from yellow to red, the human eye is not simply receiving light. It is prioritising, stabilising, comparing, estimating, and sending the brain a set of data that has already been carefully prepared. From that data, the brain builds what we call a seamless world. The more clearly we understand this, the more the central truth of the entire journey comes into focus. The human eye does not merely let us see the world, it gives the brain the clues it needs to build a world with colour, distance, motion, and meaning, deep enough for us to fully live inside it. After moving through colour, depth, motion, and all the ways the human eye helps the brain build a world we can actually live in, we can now step into a region that is even more fascinating. It is the place where vision no longer appears as a perfect power, but as something exquisitely refined and yet undeniably limited. Perhaps the most surprising thing is not how much the human eye is able to see, but how it can still create a seamless sense of reality, even though it carries within it so many gaps, biases, and natural limits. Science does not see that as failure. On the contrary, those very limits reveal how much work the brain must be doing in order to turn incomplete data into everyday experience. One of the quietest limits of the human eye is that each eye has a natural blind spot. That blind spot is not some abstract idea. It is a real region on the retina, exactly where the optic nerve leaves the eye. In that area, there are no light-sensitive cells, which means light falling there cannot be turned into visual signals the way it can in the rest of the retina. In very ordinary language, that means that in every human eye there is always a small piece of the world missing from the input. And yet most of us go through life without ever feeling that we are looking through a hole. That alone is enough to make us pause. because it means that the feeling of seeing everything completely does not always come from complete data. Very often, it comes from the visual system skillfully hiding what is missing. The strange thing is that this blind spot almost never reveals itself in everyday life. Part of the reason is that the human eyes usually work together, so the area one eye misses can be covered by the other. But even when we look with only one eye, that missing part usually does not appear as some frightening black gap in the middle of vision. Instead, the brain tends to use the surrounding information to fill in the empty area, so that a straight line may seem to continue across it, and a patterned background may still feel unbroken. The American Academy of Ophthalmology explains very clearly that the brain can fill in the missing part with what it thinks ought to be there. In other words, the human eye does not tell us that there is no data here. It works together with the brain to make that absence as unnoticeable as possible. By this point, we may begin to feel something important. The human eye does not work like a perfect camera that captures an entire scene and sends it inward untouched. A camera, in the simplest sense, has no biological way of filling in what is missing through prediction. It records whatever lands on the sensor and leaves it at that. But the human eye is different. It has a natural blind spot. It has a center and a periphery that do not function the same way. It has limits with dim light and fine detail. And after all of that, the brain still edits, connects, and interprets what comes through. That is why what we experience is not a mechanical copy of the world, but a version that has already been filtered, joined, compensated for, and organized according to the logic of the nervous system. That does not make vision less valuable. It only makes it more honest about what it truly is. If we want to see that mechanism even more clearly, visual illusions open a beautiful door. People often hear the word illusion and think of deception, as though the eyes are doing something wrong. But many neuroscientists see visual illusions as a precious tool for understanding how the brain processes images. A visual illusion is not merely a trick of a drawing. It is a moment when our perception differs from the actual physical properties of the stimulus, and that very mismatch helps researchers uncover the rules the visual system is using to interpret the world. Put more gently, each time the human eye is fooled, we learn a little more about how it is usually trying to help us see under the complex conditions of real life. Think about illusions of brightness and contrast, where two regions may have the exact same physical brightness, yet still appear different because the surrounding background is different. Phenomena like that show that the human eye and the brain do not judge the brightness of one area in isolation. They are always comparing, placing one thing beside another, weighing the surrounding light and darkness, and only then forming a final impression. Research on brightness contrast shows that center and surround computations in the visual pathway play an important role from a very early stage of processing. That explains why a grey patch can look lighter on a dark background and darker on a bright background, even though the patch itself has not changed at all. The human eye then does not read the world point by point. It always reads in relation. And when we move from contrast to perspective, the story becomes even deeper. A road stretching into the distance in a picture, two rows of trees shrinking toward the horizon, a shadow falling at a familiar angle, all of those cues cause the human eye and the brain to automatically infer depth, distance, what is in front, and what is behind. Most of the time, those inferences are extremely useful. They allow us to move through a three-dimensional world quickly and naturally without having to measure everything. But precisely because the visual system is always actively inferring the causes behind the image on the retina, it will sometimes arrive at a conclusion that does not match the actual physical structure of the picture or drawing. That is when an illusion appears. Not because the human eye is careless, but because it is doing exactly what it was organized to do, using familiar cues of light, shadow, and perspective to guess the structure of the world. There is something deeply human here. We are quick to believe that what we see is what exists out there in a direct and neutral form, but vision in the human eye has never been neutral in that sense. It always carries hidden assumptions. One of the most studied assumptions is the brain's tendency to assume that light usually comes from above. That assumption makes a great deal of sense in ordinary life on Earth, where the main natural source of light is the sun, and even indoor lighting in modern life is often placed overhead. Structural expectations like that help the human eye decode shapes more quickly, but they can also lead us astray in specially arranged images. That means vision does not rely only on what has just landed on the retina. It also relies on what the brain has learned is usually true about the world. This becomes even clearer when visual input grows ambiguous. In two-way images, blurred pictures, or situations where the lighting is uncertain, what the human eye sees can be influenced more strongly by prior experience and present expectation. Research on prior knowledge and expectation shows that perception does not move only from the bottom up, from the retina into the brain, but is also shaped from the top down by what the brain already knows or is waiting to encounter. Put gently, if the brain has a strong enough prediction about what is about to appear, that prediction can prepare patterns of sensory activity even before the stimulus arrives. The human eye, then, does not open only toward the world. It also opens toward memory, habit, and the probabilities the brain has gathered across a lifetime. That helps explain a very familiar experience that we rarely stop to notice. You walk through a dim room and momentarily think the coat draped over a chair is a person standing still in the corner. Only when you look more carefully do you realize that you guessed wrong. That does not mean the human eye suddenly became useless. It means that under conditions of limited and uncertain information, the brain tends to choose the most plausible hypothesis based on shape, memory, and expectation. Most of the time, that mechanism helps us respond quickly to the world. But sometimes it also causes us to see in the direction that makes the most sense to the brain, rather than in a way that matches the object with absolute precision. In moments like that, we realize that vision is both reception and inference. Put another way, the human eye is not lying to us. It is simply being faithful to its biology. It was built to be fast enough, useful enough, and stable enough for a living body moving through the world, not to function as a perfectly objective measuring device. It misses the blind spot because the optic nerve has to leave the eye somewhere. It uses context to judge brightness because light in the real world is always changing with its source and surroundings. It relies on prior experience because the world usually follows patterns, and the more the brain learns those patterns, the more effectively a human being can live. Seen this way, the limits of the human eye are not design flaws, they are traces of adaptation. Even the filling in of the blind spot is not simply a crude patch. Research on perceptual filling in suggests that the brain's completion of what is missing can be an active process, with measurable effects on how we experience lines, textures, and even motion passing through that region. Some studies even suggest that filling in at the blind spot can be stronger than in artificial gaps of the same size and location, which hints that the visual system may be especially optimized for this very natural physiological absence. That makes the story even more beautiful. It suggests that the human eye does not merely endure a missing piece. The eye and the brain have also learned how to live with that missing piece so gracefully that we almost never notice it was there at all. And perhaps that is also why visual illusions remain so captivating. They do not only surprise us because a still image seems to spin, or because two equal lines appear to be different lengths. They touch something deeper, the feeling that our brain is always participating in what we assume is simply seeing. Every illusion reminds us that between the light entering the human eye and the world appearing in consciousness, there is always a layer of processing, a layer of inference, a layer of priority, and a layer of expectation. When that layer works in ways that fit ordinary life, we call it normal vision. When it becomes visible in a specially designed image, we call it an illusion. But the neural reality behind those two experiences is not separate at all. The deeper we go into these quiet limits, the more trustworthy the human eye becomes in a different sense. Not trustworthy because it always gives us the absolute truth of the world, but trustworthy because it always works according to consistent rules that can be understood, studied, and that are useful for life most of the time. It gives us a version of reality stable enough to read a book, recognize a face, cross a street, drive at night, watch the sky, or remember an old room. And only when we encounter the blind spot, an ambiguous image, a deceptive background, or a misleading context do we catch a glimpse of the hidden seams in the machinery. Vision in the human eye is not a perfect mirror. It is a living construction made of biology and inference. If there is one thing worth keeping from this part of the journey, perhaps it is a gentler attitude toward our own way of seeing. When you miss a detail at the edge of your vision, when a drawing misleads your sense of length, or when something in the dark briefly becomes something else for a few seconds, that does not mean the human eye is betraying you. And from that, the central truth of the whole journey becomes even clearer once again. The human eye does not hand us the world exactly as it exists outside us. It gives the brain clues rich enough for the brain to build a world that can be understood, trusted, and lived in, even though beneath it all there are still very quiet gaps we rarely ever notice. After looking at the quiet limits of vision, perhaps this is the gentlest moment to remember that the human eye did not simply appear one day, fully complete, on our face. Long before we knew how to speak, long before we knew how to name light, the human eye had already begun forming very early in the womb. According to embryologic anatomy overviews from the United States National Library of Medicine, the first signs of eye development appear around the 3rd week of pregnancy, when the optic grooves begin to form from the developing forebrain. After that, the optic vesicle, the optic cup, the lens, and many other structures gradually emerge, and the major period of eye formation takes place most actively from about the 3rd week to the 10th week. That detail alone says so much. The human eye is not some peripheral part added onto the body at the very end, but part of the story of neural and sensory development from the earliest beginnings of life. If we go a little deeper, that process becomes even more beautiful because it shows how closely the human eye and the brain have been connected from the very start. Neurology and developmental biology sources describe how the retina develops from neural tissue, beginning with the optic vesicle, which then folds inward to form the optic cup. The inner layer develops into the neural retina, while the outer layer becomes the retinal pigment epithelium. That is why many scientists still regard the retina as part of the central nervous system brought forward toward the front of the body. Put very gently, before the human eye ever sees the world, it is already an early branch of the brain reaching outward to meet the light. And that makes the central truth of this entire story shine even more clearly. Vision has never been just about the eyeball. Even in the womb, the human eye is already being shaped as a gateway through which the brain will learn to build the world. When a baby is born, many adults look into those tiny human eyes and feel as though everything is already in place. The eyes are there, the eyelids are open, the pupils respond to light, and the face looks complete. But the visual system at birth is still not fully mature. According to the American Academy of Ophthalmology, a newborn's vision is still fairly blurry, and the entire visual system continues to develop over time, even continuing through childhood and becoming more fully mature in the teenage years. That means the human eye is not simply born and then left unchanged. It still has to learn, refine itself, and gradually synchronize with the brain and with the world. In more human terms, the human eye does not open and immediately know how to see like an adult. It grows up along with the life of the person who carries it. In the first weeks after birth, the human eye can already sense light, large shapes, faces, and movement, but the clearest range of vision is still very close. According to the American Academy of Pediatrics, newborns usually see best at about 8 to 12 inches, or roughly 20 to 30 centimeters, which is about the distance from a baby's face to the face of the person holding and feeding them. That is a beautiful fact, because the most suitable viewing distance for the newly born human eye happens to be exactly the distance of first care and first closeness. When a baby sees only dimly, yet can still keep the mother's face within the easiest range to recognize, biology seems to be quietly arranging things so that attachment can begin from the smallest details. The human eye, even in its most fragile and unfinished form, is not only learning light. It is learning faces, learning presence, learning that the world contains people who are very near. That also explains why the human eye in a newborn can sometimes look as though it is not yet fully coordinated. In the first few months, a baby's eyes may occasionally drift, wander slightly, or fail to stay fixed on the same point the way adult eyes do. Materials from both the American Academy of Pediatrics and the American Academy of Ophthalmology explain that occasional wandering in the early stage can be normal, because the baby is still learning how to use both eyes together. This wandering often decreases during the first 2 to 3 months, and if a noticeable misalignment continues clearly after 4 months, it should be taken seriously. Put more gently, the human eye at birth does not instantly become a perfectly coordinated pair. It has to learn how to see together, just as the body has to learn how to lift its head, roll over, sit up, and walk. Then, very slowly and very steadily, the human eye begins to mature through the first months of life. According to developmental milestones described by the American Academy of Ophthalmology and the American Academy of Pediatrics, by about 3 months of age, a baby can focus better on faces and nearby objects, and can also follow a moving object more effectively. By about 4 months, babies see colour better and become more interested in round shapes, high contrast patterns, and faces. By about 6 months, they distinguish objects more clearly and use visual information more effectively to recognise the world around them. After that, vision continues developing strongly throughout childhood. Sources from the American Academy of Pediatrics note that children with normal vision usually see almost like adults by about 3 to 5 years of age, and that the visual system is considered more fully mature by around 10 years old. When we hear that timeline slowly enough, we realise that the human eye does not grow only in size. It grows in its power to interpret. There is something deeply moving in that process. Before learning to read, before understanding language, the human eye has already learned to prioritise faces. The American Academy of Pediatrics notes that at a very early stage, newborns prefer to look at high contrast patterns and are especially drawn to human faces more than to other visual patterns. That is not only an interesting developmental milestone, it shows that human vision is connected to social relationship from the very beginning. The human eye does not develop in emptiness. It matures among faces leaning close, gazes being returned, and moments of eye contact between a caregiver and a baby. Before helping us read a book or drive through the night, the human eye first learned the world through faces held very near. And because that early visual system is still developing, early screening becomes especially important. Recommendations from American pediatric and ophthalmologic organizations clearly state that children need eye checks from the newborn period onward in order to detect congenital problems such as cataracts, infection, glaucoma, or abnormalities in the red reflex. In the first months, doctors observe the red reflex, the pupils, the outward shape of the eyes, and the ability to follow a face or a toy. The science here carries a very gentle quality. Because the human eye develops gradually, society has learned how to watch over it and support it from the very first days. Not to make a child anxious, but so that if something is blocking the unfolding path of vision, it can be recognised earlier. When people speak of the human eye as a personal signature, eye colour is usually the first thing that comes to mind. According to Medline Plus genetics, eye colour is the result of pigment in the iris, especially the amount of melanin in the front layer of the iris. People with more melanin, they usually have darker brown eyes, while people with less melanin, they often have lighter blue eyes. That same source also emphasises that eye colour is not determined by a single gene the way people once imagined, but is instead a complex trait influenced by many genetic variants involved in the production, transport, and storage of melanin. Put very softly, the colour of the human eye is not a simple switch between brown and blue. It is a spectrum of shades written by genetics and by the way the body handles pigment. From that same source, we also learn that human eye colour stretches across a continuous range, from very light blue to very dark brown. And that brown is the most common eye colour in the world. That detail alone brings a fascinating sense of connection. When we look into human eyes in different parts of the world, we may see different shades, but behind those differences lies the same biological principle: melanin, the iris, light, and genetics. Some people may have heterochromia, which means the two eyes are different colours, or one iris contains different coloured regions, and that can be related to genetics, eye development, or sometimes disease or injury. So even when we talk about eye colour, the human eye still reminds us that individuality is woven from very small variations within a shared biological foundation. But if we move a little closer than eye colour itself, we begin to see that the iris of the human eye differs not only in shade. The surface of the iris also contains tiny pits, contraction furrows, pigment spots, and many other microstructural details. A study published in PubMed Central describes surface features such as iris crypts, small nodules, contraction furrows, and pigment spots, and also shows that the frequency of some features can differ among populations with different ancestral backgrounds. That does not mean we can simply look at someone with the naked eye and accurately determine their origin. What it does show is that the human eye is both highly individual and still marked by a broader genetic history. A report from the United States National Research Council on Biometrics places the iris among the biological features that can be used for automated identification, and many review articles and technical studies in PubMed Central describe iris surface patterns as highly distinctive from person to person and stable enough over time to be useful in identification systems. The most careful way to say this is that the iris of the human eye is not some absolute seal that can never fail, but it is a structure with an extremely high level of individuality and enough long-term stability to become one of the most useful identifying features technology has ever learned from the human body. That makes the journey from fetus to individual identity even more beautiful. In the womb, the human eye is learning how to form from neural tissue and surface tissue. At birth, it sees only light, nearby shapes, and the first faces. In the first year, it learns how to coordinate both eyes, follow movement, understand colour, and distinguish objects. In the years that follow, it learns how to see more clearly, judge distance more accurately, and remain more stable, until finally it becomes so familiar that we forget we ever had to learn how to see at all. But alongside that learning, the human eye also gradually becomes a personal signature. Eye colour, iris patterns, the way each person's gaze appears on their face, all of it makes the eye both a biological organ and a place where others recognise who we are. Perhaps that is why the human eye moves us more deeply than many other parts of the body. We rarely say that we recognise someone by their knee or their elbow, but we recognise one another through the eyes. When a baby looks into the face of the person caring for them at just the right distance, that is not only a visual reflex, it is the beginning of the world becoming personal. Light is no longer just light. It becomes this person, this face, that smile, those familiar arms. The human eye begins in biology, but very quickly it steps into the realm of relationship, memory, and identity. And the more we reflect on that journey, the more the central truth of the whole story shines once again. The human eye does not only give the brain images of the present world, it is also the place where the brain learns what it means for a world to contain caregivers, distance, faces, colour, and familiar signs to hold on to. And once that reality has fully taken shape, the human eye becomes one of the most individual marks of that person. So when we look into the human eyes of a child or into our own eyes in the mirror on a quiet evening, perhaps the most important thing to remember is not only whether they are beautiful or not, bright or dark, brown or blue. More important than that is this: the human eye has travelled a very long journey to be there. It was once nothing more than tiny grooves in a very early embryo. It was once part of a visual system still blurry, able to clearly see only a face within arm's reach. It once had to learn how to use both eyes together, learn colour, learn distance, learn how to recognise objects. And little by little, the human eye became the place where others recognise us, where technology can identify us, and where we ourselves read the world each day. The farther we travel in this journey, the more clearly we see one quiet truth. Before the human eye helped us understand the world, it had to grow silently alongside us, so that the brain could begin building that world from the very first days of life. Once the human eye has grown alongside us, learned how to recognize faces, color, distance, and even the quiet limits of vision, there is something else happening all day long that we almost never notice. The human eye does not only see, it is also constantly protecting itself. It works through wind, dust, light, screens, long waking hours, and the body's fatigue. Yet most of the time it still keeps the surface of the eye calm enough, clear enough, and stable enough for the brain to keep building a world that feels sharp and coherent. Without that quiet layer of protection, everything we have just said about colour, detail, and depth would quickly become far more fragile. Because before the human eye can help the brain build reality, it first has to keep its own surface healthy enough for light to pass through as smoothly as possible. Tears are one of the gentlest protective mechanisms of the human eye, and also one of the most narrowly misunderstood. We tend to think tears appear only when we are sad, hurt, deeply moved, or when onions make the eyes sting. But biologically, tears are present almost all day long. The National Eye Institute explains very clearly that tears keep the eyes moist and smooth, help light focus properly so we can see clearly, and also protect the eyes from infection and irritants like dirt and dust. In other words, tears are not only the language of emotion. In the human eye, tears are also part of both optics and immunity. They soothe the surface of the eye while also keeping it smooth enough that light is not scattered too much before it travels deeper into the visual system. What's even more beautiful is that the tear layer on the human eye is not just a simple sheet of water. The National Eye Institute describes the tear film as having three major parts: an oily outer layer that helps keep tears from evaporating too quickly and makes the eye's surface smoother, a watery middle layer that helps keep the eye moist and nourishes eye tissue, and an inner mucus layer that helps the tears cling to the surface of the eye. When we hear that slowly enough, we realise that even something as small as the eye not feeling dry is actually the result of several layers working together. The human eye does not only need moisture, it needs a carefully structured coating that can stay in place, resist evaporating too quickly, and remain smooth enough for light to pass through gently. If one of those parts is not doing its job well, stinging, grittiness, irritation, or brief blur can begin to appear. And this is exactly where blinking comes in as a movement so small it is almost invisible, yet incredibly important to the human eye. Every time we blink, the tear film is spread evenly across the surface of the cornea. The National Eye Institute states very clearly that each blink spreads a thin layer of tears across the cornea, and then the tears gradually drain through tiny openings at the inner corners of the eyes and down into the nose. That detail alone explains two familiar things in daily life. First, blinking is not some unnecessary movement. It is more like a gentle wiping and refreshing of the visible surface of the human eye. Second, when we cry a lot and tears run into the nose, that is not random at all. It is because the tear drainage system of the human eye has been connected to the nasal cavity from the very beginning. Perhaps because blinking happens so often, we almost never think of it as real labour. But if the surface of the human eye were not being refreshed constantly in that way, vision would quickly become less comfortable. A stable tear film helps keep the surface of the cornea smooth and clear, while a tear film that breaks apart too easily can leave the eyes feeling gritty, burning, briefly blurry, or more sensitive to light. The National Eye Institute even uses tests that measure how long a person's tear film remains stable after a blink, because that stability is directly related to dry eye disease. Put gently, the human eye does not only need tears to exist, it needs tears that can stay on the eye's surface long enough instead of disappearing too quickly in the middle of long working hours. That's exactly why dry eye becomes one of the most common experiences, especially as people get older. The National Eye Institute explains that dry eye happens when the eyes do not make enough tears to stay moist, or when the tears do not work properly. This condition can cause discomfort and sometimes affect vision. According to that same source, dry eye is common and affects millions of Americans, with a higher risk in people age 50 and older. That is not meant to make the audience anxious. It simply helps reveal something deeply human. The human eye may appear resilient, but its surface is actually very delicate. As soon as the tear film stops working as smoothly as it once did, the whole experience of the world can begin to change, from a mild sting while reading to the feeling that a tiny grain of sand is sitting in the eye. What is worth noticing is that dry eye does not only mean not having enough tears. The National Eye Institute explains that dry eye can happen because the tear glands do not produce enough tears, because tears evaporate too quickly, or because the quality of the tears is not good enough to do the job. Medline Plus also lists familiar symptoms such as burning, redness, a gritty feeling, sensitivity to light, and blurred vision. So when the human eye feels dry, the problem is not necessarily just about quantity. It may be that the outer oil layer is not holding moisture well enough, that the middle watery layer is not thick enough, or that the eye's surface is no longer being evenly coated the way it once was. That small discomfort we may dismiss as momentary fatigue is sometimes really a sign that the protective layer on the surface of the human eye needs support. One of the situations that most easily reveals that fragility is when a person stays focused on one thing for too long. The Centers for Disease Control and Prevention reminds us that when we spend a lot of time at a computer or staring at one task, we sometimes forget to blink, and that can lead to eye strain or tired eyes. The National Eye Institute also clearly states that dry eye can happen if someone spends a lot of time looking at a computer, tablet, or smartphone. Put more softly, the human eye can work for us for a very long time, but modern concentration can unintentionally steal away the eye's natural rhythm of self-care. When we sink into a document, a film, or a phone screen for hours, what disappears first is sometimes not focus, but the natural blink rate needed to keep the eye's surface calm and moist. Most people have probably experienced this without naming it. After a long afternoon of reading or staring at a screen, the human eye may begin to sting, feel heavy, seem as though a thin layer of dust is resting on it, or become briefly blurry before clearing again after a few blinks. That does not necessarily mean the eyes have become weaker for a few hours. It means the surface of the eye is speaking up. A Centers for Disease Control and Prevention resource on computer vision syndrome describes burning or aching eyes as something that can happen because of dry eye when screen use leads to less blinking. Once we understand that, we begin to see how honest the human eye really is. It does not stay silent forever. It has very gentle ways of telling us that the tear film is getting thinner, that the corneal surface needs a small break, and that the body has been using the eyes too long without letting them return to their natural rhythm. That is why the advice from the Centers for Disease Control and Prevention sounds so simple, yet fits the biology of the human eye so well. They suggest the 20-20-20 rule: every 20 minutes, look at something about 20 feet away, which is about 6 meters, for 20 seconds. The heart of that advice is not some magical trick. It is a reminder to restore the natural rhythm of shifting focus and blinking that intense concentration tends to stretch too far. In a world where so many people live among screens, this is almost like a polite way of giving the human eye back part of the breathing room it naturally needs. Vision was not meant to be nailed to one distance, one light source, and one glowing flat surface without interruption. It needs little pauses so the protective layer on the surface of the eye can be refreshed, so the focusing system can relax a little, and so the brain can receive a wider visual frame again. Alongside blinking and visual breaks, sleep also appears as a very quiet form of protection for the human eye. In its guidance for reducing discomfort from dry eye, the National Eye Institute recommends getting about 7 to 8 hours of sleep each night. That advice alone says something very important. Caring for the eyes is not only about using drops or avoiding wind and dust, but also about the resting rhythm of the whole body. When we sleep enough, the body has time to reduce overall strain, stabilize the eye environment, and help lessen dryness, fatigue, and irritation for many people. In a tone very much in the spirit of Sleep by Knowledge, the human eye does not only need light in order to work, it also needs enough darkness and enough deeply closed hours to recover its natural calm. Research in visual neuroscience on sleep deprivation suggests that the story does not stop with dryness or tiredness. One study published in PubMed Central found that acute sleep deprivation can reduce performance on visual tasks that require more detailed processing, while another study showed that after sleep loss, the coordination between the two eyes when tracking a moving target also becomes weaker. These findings do not mean that staying up late for one night will ruin the human eye. What they suggest is much gentler than that. When the body is short on sleep, it is not only general alertness that declines, but also the more delicate layers of coordination behind vision. The brain builds the world less smoothly, and the two eyes do not work together quite as gracefully as they do when they have been properly rested. And so, once again, sleep appears as a quiet ally of vision. There is one more very familiar detail that many people notice only when they wake up. In the morning, the human eye can sometimes feel gritty, dry, or more uncomfortable than usual. Medline Plus notes that in some people, dry eye symptoms are connected to sleeping with the eyes slightly open. That may sound like a small thing, but it shows just how delicate the eye's surface really is. Simply being fully covered or not fully covered during sleep can make a difference. The human eye may seem strong on the outside, but the cornea and tear film actually depend on very precise conditions. Enough moisture, enough coverage, enough blinking while awake, and enough rest while asleep. When those conditions shift, even slightly, mild discomfort can appear as a reminder that the eyes need a little more care. And when we gather all of these seemingly small things together, we begin to see a very gentle picture. Tears are not only for crying. Blinking is not just an unnamed reflex. Taking breaks from screens is not just polite advice. Getting enough sleep does not only help us feel less tired the next day. All of these things are protecting the human eye in quiet but decisive ways. They keep the eye's surface moist and smooth, so light can pass through more cleanly. They help prevent the tear film from disappearing too quickly. They reduce strain, grittiness, and the small imbalances that can build up after long hours of wakefulness and near work. And because of that, the brain can keep receiving material that is clear enough to build a stable world. So the central truth of this whole journey becomes visible once again. The human eye does not only give the brain data about the world, it also has to care for itself quietly every minute so that the data stays clean enough, stable enough, and gentle enough for life to go on. Perhaps the gentlest thing worth keeping from this part is this: the human eye has worked for us from morning until night with almost no complaint. It has endured wind, dust, blue light, small print, dark roads, dry rooms, air conditioning, long reading hours, and even those times when we forget we are asking too much of it. And still, it tries to keep each morning clear enough to see, each familiar face still there, and each line at the end of the day steady on the page. Once we understand how tears, blinking, and sleep have worked together to protect the human eye, we stop seeing visual comfort as something automatic. We begin to see it as the result of many small acts of care, repeated constantly and almost silently. And perhaps tonight, by blinking a little more slowly, stepping away from the screen a little earlier, and giving your own human eyes a more decent night of sleep, you may be returning a small part of the gentleness they have been offering you every day. After all those quiet layers of tears, those almost invisible blinks, and those hours of sleep that help soothe the surface of the eye, the human eye enters another stage that nearly everyone will one day pass through. This is the stage of time. But time, in this case, should not be told as though it were some force that ruins vision. Telling it that way would be neither accurate nor fair to the human eye. More truthfully, the human eye changes with age because it has worked without stopping for decades, received light billions of times, helped us read, drive, recognize faces, look at the sky, find each stair step, and move through so many passing years. Once we understand aging in that way, it no longer feels like betrayal. It feels like the mark left on an organ that has served faithfully for a very long time and is still trying to do its part. One of the most familiar changes in the human eye is that seeing up close gradually becomes harder. The National Eye Institute explains that this is a normal part of aging, and it usually begins after age 45, when the lens inside the eye becomes stiffer and less flexible, so it can no longer change shape as easily as before in order to focus light correctly onto the retina when looking at nearby objects. That is why so many people one day suddenly realize they have to hold the menu farther away, move the phone back, or squint at a medicine label, a receipt, or fine print. What matters here is that, in that moment, the human eye is not becoming weak in any simple sense. It is simply entering a stage in which the mechanism for focusing up close is no longer as soft and effortless as it once was. In truth, the feeling of having to hold your phone farther away is one of the most ordinary and honest signs of aging in the human eye. The National Eye Institute explains very clearly that when close vision declines with age, people often need to hold reading material farther away in order to focus, may experience more eye strain, and may sometimes get headaches if they try to do close work for too long. That same source also notes that this change is so common that almost everyone experiences it, and that it usually progresses gradually over time before slowing down after about age 65. There is something gently reassuring in that. The human eye does not change all at once like a door slamming shut. It changes little by little, slowly enough for us to learn new adjustments, like increasing the font size, improving the lighting, or using reading glasses when needed. Many people also notice that the very same page they could once read comfortably under dim light later begins to require brighter light in order to feel easy on the eyes. That fits perfectly with what the National Eye Institute and the National Institute on Aging describe. As the human eye grows older, near vision becomes harder not only because the lens becomes less flexible, but also because other changes in the eye's optical and sensory systems make comfortable vision depend more on favourable lighting conditions. So all the small adjustments of daily life, like turning on an extra reading lamp, enlarging the text, or choosing stronger contrast, are not signs of surrendering to age. They are ways of cooperating with the human eye in its new stage of life. And when we speak of light, another change in the human eye often feels even more frustrating. Glare becomes more bothersome, and adjusting to changes between light and dark no longer happens as quickly as before. Medline Plus notes that by about age 60, the pupil may be only about 1/3 the size it was at age 20, and that its response to bright and dim conditions also becomes slower. The National Institute on Aging also emphasises that older adults often need more time to adjust to changes in lighting. Put very simply, when the human eye grows older, it does not only make close reading harder, It also makes the transition from a bright room into a dark hallway, or from a sunlit street into a garage, feel slower than it once did. That is also why driving at night often becomes more tiring with age. Medline Plus notes that older adults may become less tolerant of glare and may have more difficulty with darkness and bright light, and that those problems with brightness and darkness can make night driving harder. Information from the National Eye Institute about cataracts also explains that glare from headlights, streetlights, or strong light can become more noticeable, along with poorer night vision and sometimes halos around lights. When we place those details side by side, we can see very clearly that the human eye at night is not just tired in some vague emotional sense. It is truly processing light through a system that has become less flexible and more easily disturbed by harsh sources of brightness. A gentler change, but still a very real one, is that colour can begin to look different. The National Institute on Aging says that as people grow older, they may have more trouble telling certain colours apart, such as blue from black. Medline Plus also notes that with age, the lens can become more yellow, and that telling blue from green apart can become harder than telling red from yellow apart. That may sound like a small thing, but if we listen closely, it feels deeply human. The human eye does not only become less sharp when reading fine print, it can also make the colour of clothing, the colour of a stare, or the colour of an object in dim light feel less clearly separated than before. The world does not exactly lose its colour, but the human eye begins to need more light and more contrast in order to read the world through colour as it once did. Medline Plus also describes a series of other quiet structural changes that happen in the human eye over time. The lens becomes more yellow, less flexible, and gradually a little cloudy. The cornea becomes less sensitive, the eye muscles become less able to rotate fully, and the vitreous gel inside the eye begins to shrink. When reading descriptions like that, we should not picture the human eye as something collapsing into failure all at once. More truthfully, this is a living system whose material properties are gradually changing after many years of use. The lens is no longer as soft as it once was. The pupil no longer widens as quickly as it did in youth. Some tissues become less elastic, and out of those very slow physical changes, everyday visual experience gradually begins to feel different. Among age-related changes, cataracts deserve to be described in a calm voice. Information from the National Eye Institute explains that cataracts happen when the lens becomes cloudy because proteins in the lens clump together, and the risk increases with age. That same source also notes that age-related cataracts may begin as early as the 40s or 50s, but during middle age they are often still small and may not noticeably affect vision. In many people, it is only after age 60 that they begin to cause more obvious visual problems. So when the human eye ages, that does not mean growing older automatically means seeing poorly because of disease. Many changes begin very early, but so slowly that we do not truly feel them in daily life until much later. Cataracts also help explain why so many people notice that other drivers' headlights feel harsher at night. Colours seem more faded, or the world starts to look as though it is being seen through a thin veil of mist. The National Eye Institute lists common cataract symptoms such as blurry or cloudy vision, faded colours, glare, halos around lights, worse night vision, and the need to change glasses more often. What is subtle here is that some of these changes sound very much like just getting older, when in reality they may reflect a specific change in the lens of the human eye. That is why the best tone here is not fear, but discernment. Some things are common changes of aging, while other things deserve to be checked so we can know exactly where our own eyes stand along that path. Another detail of aging that many older adults notice is the appearance of tiny floating shapes drifting through their vision, often called floaters. Medline Plus explains that as age increases, the jelly-like substance inside the eye begins to shrink, which can create small particles called floaters in the field of view. Most of the time, they do not cause a loss of vision. But Medline Plus also emphasises that if floaters appear suddenly or increase quickly in number, the eye should be checked, because this can be a sign of retinal detachment. This is a very important example of the line between what is common with age and what deserves medical attention. The human eye goes through many normal changes over time, but normal never means that every new change should simply be ignored. The National Institute on Aging offers a distinction that is especially valuable for older audiences. Changes such as losing the ability to see clearly up close, taking longer to adjust to different levels of light, or having more trouble telling certain colours apart can be normal changes of ageing, and they can often be improved with glasses, contact lenses, or better lighting. But at the same time, that source also warns that some signs are true eye emergencies, such as sudden vision loss, many new floaters or flashes of light, eye pain, double vision, or redness and swelling in the eye or eyelid. This is the National Eye Institute emphasises that a dilated eye exam is the best way to detect eye disease early, even when there are no clear symptoms yet. That source recommends having this kind of exam every 1 to 2 years after age 60, and more often for people with risk factors such as diabetes or high blood pressure. When we look at this in a humane way, it does not feel like a frightening command. It feels perhaps the most deeply relatable part of this whole story is this. Many changes in the human eye as it ages do not mean that life must shrink. The National Institute on Aging says quite clearly that these common changes can often be corrected with glasses, contact lenses, and better lighting, helping people maintain an independent lifestyle. That sounds simple, but it touches exactly the quiet fear many people carry after 40, 50, or 60. The fear is not only, are my eyes aging? It is, will I still be able to read, drive, move around on my own, and keep living the life that feels like mine? And the answer is often far less bleak than people fear. The human eye changes, but human beings also have many ways to adapt along with it. At a deeper level, aging reveals the central truth of this entire journey more clearly than ever. Later in life, that very data begins to change too. Near things become blurrier, nighttime glare grows harsher, colours separate less clearly, halos appear more easily, and adaptation to changing light becomes slower. But the brain continues doing its work. It continues trying to build a world out of those changed signals. So if one day you realise that you need to hold the newspaper farther away, need brighter light to thread a needle, feel less comfortable on the road at night, or need a few extra seconds for your eyes to adjust to darkness, perhaps the gentlest thing to do is not to take that as proof that the human eye is abandoning you. See it instead as an honest reminder that it has worked for a very long time and is now shifting into another way of being. Whatever can be helped with glasses, better lighting, or regular checkups, give your human eyes that support. And whatever changes suddenly, hurts, distorts, darkens, flashes, or fills with an unusual burst of floaters should be taken seriously. Because maturity in living with the human eye does not mean ignoring every change. It means learning the difference between the natural rhythm of aging and the kind of signal that needs to be answered in time. In the end, perhaps this is the most important thing to keep before we move on. The human eye grows older not because it has stopped loving the world, but because it has looked at the world for so long. It has stayed awake through the first mornings of youth, read pages through the busiest years of life, watched familiar faces grow older beside us, endured hospital lights, nighttime headlights, kitchen lights, afternoon sunlight, and long working hours in front of a screen. And if now it needs more light to read, a pair of glasses to see up close, or a few extra minutes to adjust to darkness, that is not failure. It is the sign of an organ that has lived a very real life. And the more we understand that change through science, the more gently, deeply, and maturely we can look back at our own human eyes with respect. By the time we arrive here, the human eye begins to appear as something more than an organ resting in its socket, nourished by blood, protected by tears, changed by age, and sending signals back to the brain. It also lives another life beyond pure biology. The human eye enters civilization, medicine, communication, memory, and even technology. There may not be many parts of the body that are at once so private and so public. The heart beats deep inside the chest. The lungs expand and contract in silence. But the human eye sits right before another person, where someone else can read presence, attention, tenderness, avoidance, empathy, or simply whether a person is truly here with them at all. And perhaps that is why, for a very long time, human beings have not used the human eye only to look at the world. Human beings have also used it to look at one another. In the science of social attention, the direction of the gaze carries a special weight. A major review on PubMed Central describes how gaze processing helps create joint attention, and how eye contact is often the opening step by which two people begin directing their attention toward the same object or idea. Put gently, The human eye does not only gather light for the person who is looking, it also sends a signal to others about where that attention is going. When one person looks toward a door, the person beside them often looks there too. When a baby sees an adult looking at a toy, the baby tends to learn how to share attention toward that same point. Through gaze direction alone, the human eye can draw two brains close together within the same scene. That helps explain why a gaze can feel so powerful in face-to-face communication. That same review also notes that eye contact is a stimulus human beings give priority to in social cognition, and that becoming the object of another person's gaze can have a clear emotional impact. When someone truly looks at you, the human eye is not only sending information about pupil position or the angle of the head, it is sending something deeper. I am giving my attention to you right now. Perhaps that is why, in conversation, the difference between a passing glance and a fully present gaze can completely change the quality of the moment. Other studies on PubMed Central also show that eye contact is a powerful social signal connected to attention, closeness, emotion, and the quality of interaction. A study published in 2022 describes quite clearly that eye contact is an important social skill that helps create connection between people who are interacting, and when eye contact is blocked, the feeling of closeness between them also becomes weaker. This feels very close to ordinary life. When someone looks at you with open, direct, and calm eyes, you may feel acknowledged as a person who is truly present. But when that gaze constantly drifts away or is hidden, the sense of connection often becomes thinner. The human eye then is not only the place where light enters, it is also the place where relationship begins to take shape. Perhaps because the human eye reveals attention and presence so strongly, it is often treated as a symbol of awareness itself. That is a fairly natural conclusion drawn from vision science and social science. We do not look at a knee to guess what another person is focusing on. We do not look at an elbow to decide whether someone is welcoming us or withdrawing from us. We look at the eyes. Gaze direction tells us the object of attention. Eye contact signals presence. A returned gaze can open the door to joint attention, emotional synchrony, and a feeling of connection. So when human civilization gives the human eye a symbolic role in recognition, awakening, or truly seeing something, perhaps civilization is only expressing in symbols what biology and neuroscience have already expressed in data. What is fascinating is that the human eye also does something else very quietly in communication. It helps us judge not only where another person is looking, but how much presence they are bringing to the encounter. A face may be smiling, the words may be polite, but if the eyes keep drifting elsewhere, we often feel absence in the middle of the conversation. On the other hand, a steady and calm gaze often makes words feel more sincere. Researchers studying gaze cueing have shown that the direction of the eyes can pull another observer's attention quickly and almost automatically. That means the human eye does not only communicate social information at the conscious level, it also helps guide another person's attention at a very rapid level, almost like a reflex. So when we say that the human eye belongs to civilization, we're not speaking only of poetry or symbolism. We're speaking of the entire way human beings live together. A baby learns joint attention through gaze direction. An adult reads goodwill, hesitation, or empathy through the eyes. A sincere conversation usually carries a different quality of eye contact than a cold and purely social exchange. A doctor, a caregiver, a friend, a person in love, all of them in one way or another rely on the human eye to sense whether they are truly being seen. And in that way, the human eye no longer belongs only to anatomy. It steps into the realm of social life. Modern medicine, in one very beautiful sense, is civilization's effort to accompany the human eye throughout that journey. When vision is no longer clear enough because of refractive error, the National Eye Institute explains that eyeglasses are the simplest and safest way to correct it. Contact lenses can rest directly on the surface of the eye to correct refractive error, and some surgeries can reshape the cornea to improve the way light focuses. Put gently, medicine does not force the human eye to remain perfect forever. Medicine builds bridges. When the eye and light no longer meet as they once did, human beings use glasses, contact lenses, and surgery to help the human eye continue giving the brain a clearer world. Among those bridges, cataract surgery may be one of the most humane examples. The National Eye Institute explains that a cataract is a cloudy area in the lens of the eye and that surgery is the only way to remove it. During the procedure, the doctor removes the cloudy lens and replaces it with an artificial lens. That same source also says that about 9 out of 10 people see better after surgery, and many people notice brighter colour as well because the artificial lens does not have the same obvious yellow-brown tint as the natural lens that had grown cloudy. That is a beautiful detail. Human civilization does not only extend life, in many cases it also gives the human eye back some of the light that had grown dim with time. If glasses and surgery are ways of helping the human eye continue doing its optical work, then a dilated eye exam is the way medicine learns how to look deep into the eye itself. The National Eye Institute states very clearly that a dilated eye exam is the only way to check for many eye diseases in their early stages, when they are easier to treat and before they cause vision loss. That guide also explains that this is a simple and painless procedure in which the doctor uses eye drops to widen the pupil, making it easier to see the back of the eye. Put simply, civilization does not only help the human eye look outward, it also learns how to look back inward into the human eye in order to notice things the patient may not yet feel at all. And in that inward look, the eye becomes a very special medical window. MedLen Plus explains that when the pupil is dilated, a doctor can observe the retina, nearby blood vessels, and the optic nerve at the back of the eye. That same source notes that a standard eye exam can help detect not only cataracts and glaucoma, but also diabetes, high blood pressure, age-related macular degeneration, blood vessel damage, and many other abnormalities. The National Eye Institute also emphasises that people with diabetes or high blood pressure often need regular dilated eye exams, and that diabetic retinopathy may have no early symptoms even after it has begun affecting the blood vessels of the retina. So when we say the human eye is a window into health, that is not just a poetic phrase. In the retina and the eye's vascular system, doctors can truly see traces left behind by disease throughout the body. This becomes even clearer in hypertensive retinopathy. The StatPearls resource from the United States National Library of Medicine explains that uncontrolled high blood pressure can damage multiple target organs, including the retina, with changes in blood vessels and nerve tissue that can be seen on examination or imaging. That source also notes that hypertensive retinopathy can reflect the burden of systemic disease and is associated with the risk of complications throughout the body. That means the human eye does not only give us light and colour, it also gives medicine one of the rare places where blood vessels and nerve tissue can be directly observed without surgery. That is why the human eye is both an organ of sight and a place where doctors can read part of the story of the whole body. If medicine has learned to look inside the human eye in order to protect vision and health, then modern technology has learned from the eye's uniqueness in order to identify human beings. The National Institute of Standards and Technology has an entire series of programs for evaluating and standardizing iris recognition. Its overview page on Iris Exchange explains that the program was launched to expand iris recognition capability and support the market for iris-based applications with standardized, interoperable images. Put in simpler terms, technological civilization has realized that the iris pattern of the human eye is rich enough in detail and useful enough to serve as a foundation for automated identification. A living part of the body, something we once experienced mostly through eye colour and gaze, has now become the subject of standards, algorithms, and matching systems. That does not make the human eye any less human. On the contrary, it shows that the farther technology advances, the more it has to learn from biology. In iris recognition, these systems do not invent a new structure. They rely on the very details nature already placed in the human eye. In retinal examination, doctors do not create a new window into the body. They simply learn how to use the one that was already there. In lens replacement surgery, medicine does not create new light. It only helps light pass through the human eye more easily. The more we look at this entire journey, the more we see that civilization and technology at their best are not replacements for the body. They are refinements that help the body continue living with the qualities it already possesses. Perhaps that is also why the human eye carries a meaning far deeper than that of a biological sensor. The eye is where others know we are present. The eye is where small children learn to follow the gaze of adults and share attention with the world. The eye is where doctors can see blood vessels, the retina, nerves, and signs of disease before illness begins speaking clearly. The eye is where medicine places glasses, lenses, eye drops, surgery, and diagnostic tools. The eye is where technology finds a pattern distinctive enough to use for identification. And the eye is also where memory often returns when we remember a person, not only because their eyes were beautiful, but because those human eyes once looked at us in a way no one else ever could. When we bring all of that together, the central truth of this entire journey shines one last time here in the body of the story. The human eye does not only help the brain receive light in order to build physical reality, it also helps human beings build social reality. Through gaze, another person understands what we are attending to. Through eye contact, two people step into the same shared space of attention. Through eye exams, doctors read signs of disease throughout the body. Through glasses and surgery, vision is extended a little farther. Through the iris, technology learns how to recognize each individual. All of it is saying the same thing. The human eye does not belong only to the body, it belongs to relationship, memory, civilization, and the way human beings are present with one another in the same world. And perhaps, if there is one quiet feeling worth holding on to before we arrive at the final truth, it is this. Every day, the human eye does something for us that is greater than simply seeing. It turns a stranger into someone familiar. It turns attention into encounter. It allows a doctor to see what the cardiovascular system or blood sugar is leaving behind in the retina. It turns a simple pair of glasses into a bridge back to the page. It allows a small surgery to return brighter colour to old age. And it allows a ring of iris to become a sign that one human being is truly themselves and no one else. Once we understand that, we no longer look at the human eye as two organs placed on the face. We begin to see it as the place where the body, the brain, society and civilization touch one another in a way that is quiet, deep and profoundly human. After everything we have just travelled through, the 101st truth about the human eye turns out to be both the simplest and the deepest. The human eye does not only let us see the world out there, the human eye also reveals how a human being exists within that world. Limited, because our way of seeing will always have boundaries. Interpretive, because what we see is always the result of light passing through the cornea, the pupil and the lens, reaching the retina, being turned into signals, and then being quietly assembled by the brain into a reality that carries meaning. Fragile, because if the surface of the eye becomes dry, if the lens changes with the passing years, or if the light grows too harsh at night, the entire experience of seeing can begin to change. But it is also full of wonder, because from all of those limits, the human eye still has the power to open up the sky, a face, a road, a page, the light at the end of the day, and even the memories we carry for a lifetime. We have gone through a very long journey, from the first transparent layer of the cornea receiving light, to the pupil quietly adjusting it, to the lens patiently bringing things into focus, to the retina where light first begins to turn into the language of the nervous system. We have looked into rod cells and cone cells, into the sharpest region of the human eye, into the way colour, depth, motion, and darkness are created. We have also moved through the quiet limits of vision, where the brain has to fill in the blanks, where sight is not a perfect copy of the world but a delicate construction, trustworthy enough for us to live, to love, to recognise one another, and to keep moving forward. Then we went farther still, into the earliest years of life when the human eye was still learning how to receive light and faces, into tears, blinking, and sleep, into aging, into the deeply human changes brought by time, and finally into the place where the human eye steps beyond pure biology and enters civilization, communication, medicine, technology, and the meaning of life. But after all of that, the greatest truth is not how complex the human eye is. The greatest truth is that the human eye has quietly accompanied the entire life of a human being. It is there on the first morning we open our eyes to the world. It stays with us through the first faces that bend down to look at us. It holds the years of reading, the afternoons spent by the window, the familiar roads, the nights of driving, the emotional moments, the times we looked for a long while without needing to say a word. And then, as the years pass, the human eye grows older with us too, not as a betrayal, but as the mark of an organ that has lived a very real life, that has seen so much, that has worked without rest so the brain could go on building this world day after day. If there's one thing that remains after this journey, perhaps it's the feeling that vision is not perfect, and that is exactly why it's even more astonishing. The human eye does not give us reality in the cold, mechanical way a machine would. It gives us a world that has been filtered, stabilized, interpreted and gently preserved accurate enough for us to trust, and gentle enough for us to live inside as human beings. And now, if your human eyes have begun to grow tired after this long journey, then perhaps it is time to let them rest. Let the light soften. Let your eyelids close a little more slowly. Let the brain stop building any more images tonight. Thank you for staying with Sleep by Knowledge on this very quiet journey. I wish you a night that is deep, peaceful, and full of rest. And I will see you again on the next journey.